table containing 11 entries. Now we will add each of the elements one by one into this hash table. The first element, 40. 40, we will take the hash function 40 modulo 11. I think we get a 7. As a result, we're going to store 40 here. Remember, in each cell, we have a linked list. Well, in this question, we're talking about separate chaining. So when multiple elements are mapped into the same cell, we're going to use a linked list to store all of them. So at the very beginning, when the hash table is empty, then we have 11 empty linked lists. And after inserting 40, we're going to have 40 modulo 11 giving us 7, telling us that 40 should be stored at index 7. So now we have the linked list. This linked list will have one single element, 40 here. The next element, 60. 60 modulo 11, I think we get a 5. So 60 will be stored here. Then next one, 37. 37 modulo 11, I think we get a 4. So we'll have 37 stored here. And then next one, 84. 84 modulo 11, I think we get a 7. Another 7, so we add 84 here. It doesn't matter too much if we add it at the beginning of the linked list or end of the linked list. In my case, I will just add it at the end of the linked list because I think it's easy to write on my screen. Next element, 42, modulo 11, I think we get a 9. So 42 will be inserted here. And then for 18, we get another 7, so 18 is here. The last element, 30 modulo 11, we get an 8. And then we have 30 inserted here. So this would be our hash table after inserting all these elements one by one. And clearly, some of the cells are still empty, and then we have some of the cells, I think at least for index 7, we have 3 elements stored in it. Now, if we are looking for an element, what we are going to do is we're going to apply the same hash function on the element we are looking for. Because by applying this hash function, it tells us if the element is in the hash table, where can we find it? For example, if we are looking for 100 in this hash table, we know it's not in it. So how do we search for it? We're going to apply the hash function 100 modulo 11, and the answer is 1. So if 100 is in this hash table, we can find it in the linked list at index 1. And now if we jump to index 1, we're going to see an empty linked list. So we know 100 is not in this hash table. And if we're looking for element like 40, then 40 modulo 11, we get a 7. Then we go through the linked list to find out where the 40 is there. In this case, we can find it in just one comparison. But if we're looking for 84 or 18, we will need 2 or 3 comparisons. So in the second question here, it says, find the largest number of key comparisons in a successful search. Successful search means we are searching for an element that's indeed in the hash table. And I think the maximum number of comparisons here would be 3 if we are searching for element 18. When we are searching for 18, we get a 7, then we will need to go through the entire linked list before we find 18. And the last question here is find the average number of key comparisons in a successful search in this hash table. So in this particular hash table, if we are looking for 37 as a successful search, we will only need 1 comparison. If we are looking for 60, 1 comparison. If we are looking for 40, 30, 42, it's also 1 comparison. But if we are looking for 84, we will need 2 comparisons. And if we are looking for 18, 3 comparisons. And the average for all of these 7 elements would be 1 comparison plus 1 plus 1 plus 1 plus 1 plus 2 plus 3 divided by 7 elements in total. I think that's 10 divided by 7. So that's the average number of key comparisons in a successful search in this particular hash table. So that's one way of dealing with collisions. We have all the elements that mapped into the same cell stored in a linked list. And the second possible approach for dealing with the collisions would be we can use a closed hash table. In a closed hash table, the hash table would be strictly an array. So each cell will only store one single element. We cannot store multiple elements like a linked list. So let's try to insert the same set of elements one by one using the same hash function. So 40 modulo 11, we get a 7, so 40 will be stored here. 60 modulo 11, we get a 5. Then 37 modulo 11, we have a 3, right? We have a 4, sorry. That's 37. The next one, 84 modulo 11, we get another 7. But since now 7, the cell at index 7 is already occupied. So what we do is we will find the next available cell. So starting from index 7, we'll move to the next one, index 8. And since this is empty, so we're going to place the new element 84 here. Then the next element, 42. 42 modulo 11, we get a 9. So we're going to place 42 here. Then the next one, 18. 18 modulo 11, we get a 7 again. But since the cell at index 7 is occupied, we check the next one, index 8. It's also occupied. The next one, index 9. The next one, index 10. So we will eventually have the element 18 inserted here. And then for the last element, 30. 30 modulo 11, we get 8. So we will need to check index 8, index 9, index 10. And since we reach the end of the hash table, we come back to the beginning. And here is the empty cell, so we will have the last element 30 inserted here. So that would be the closed hash table we construct by inserting these elements into the hash table. Now, if we are looking for the number of key comparisons in a successful search, well, I think we will simply try to say when we are searching for each of these elements, how many comparisons are we going to make? So the first element, 40, we get a 7 and find it immediately. So I think we'll just need one comparison. And for 60 and 37, I think we'll also need just one single comparison. Then for 84, since we get 7 from the hash function, but we find it at position 8, so we will need 2 comparisons. And for 42, 42 modulo 11 is 9, so we will only need one comparison. And for the last 2 elements, 18 and 30, I think for both of them, we will need 4 comparisons. So the maximum number of comparisons in a successful search would be 4 if we are searching for 18 or if we are searching for 30. And the average number of key comparisons in this particular hash table would be 2. Well, that's the number of comparisons for searching each of these elements, add up together and then divide by 7 because we have in total 7 elements. We also discussed double hashing in the lecture, but we don't have a question here in the tutorial. But I think the idea is pretty straightforward. We're also using a closed hash table, but whenever we find a collision, rather than move to the next available cell one by one, we are going to jump for a few steps, and the number of steps is determined by the second hash function. So I think you can easily understand it by going through the lecture material. And if you have any questions, feel free to make use of the discussion board. So today we've discussed the host pool string search algorithm, and we used a couple of examples to see that it's performing better than the brute force string search algorithm. And then we also had these 2 questions talking about the hash table, and we discussed 2 general ideas of dealing with the collisions. So I think that's pretty much everything that we should discuss today. Thanks for joining us, and I'll see you next week. A question from the chat window. Searching for 30 takes 4 steps. 30 modular 11 giving us 8. So we check for index 8, 9, 10, 0. So that's 4 comparisons. Question 73C is, the answer is 2. I think the answer is 2. Searching for 37, 60, 40, and 42 takes 1 comparison. 84, 2 comparisons, then 18 is 4, and then 30 is another 4. So 1, 2, 3, 4, 5, 6, 10, 14. Yeah, 14 total comparisons shared by 7 elements. So 2 comparisons in average. Thank you, everyone.
What will happen if the input we want to search is larger than this index table? So we don't have room for, yeah.
Sorry, your question again?
Well, what if the input we are trying to search, so the numbers we are trying to store in this hash table is larger than the index? So it's
we have 11 empty cells, and I think your question is, what if we have 12 or 13 elements that we want to insert into this hash table?
Yeah, and it's close.
Yeah, well, clearly we can't insert more than 11 elements because we only have 11 available cells. So usually for a hash table, in practice, a hash table we usually have, or will commonly have, a load factor of roughly 0.1, 0.2. So if you already know the size of the hash table, I mean, if you already know how many elements that you want to insert into a hash table, then you're going to adjust its size, its total available cells accordingly. For example, if you know you're going to have 1,000 elements added into the hash table, and you want to have the load factor being 0.1, then when you initialize a hash table, you're going to have 10,000 empty cells.
Okay.
And of course, at the same time, you're going to choose a good enough hash function. So the hash function we discussed in the lecture, where we're just going to use a simple modular function, it's not a good hash function in practice, but it's theoretically a working hash function because it maps any integer into a range between 0 and 10, well, if we are taking modular 11.
I see, yeah. So there are a lot of other hash functions out there.
There are many other hash functions, and in practice, I think in different programming languages, you don't need to worry about the actual hash function they used. It should be far more complicated than you can imagine. But the idea is that we want to have any random element